Our first talk of the day is a keynote by Dr. Frank Wood. He used to be an entrepreneur and then became a professor at Columbia and is now leading the department at Oxford.
Good morning. Can everybody hear me okay in the back? Yeah? All right, so yeah, my name is Frank Wood. I work on probabilistic programming. I'm a professor in the engineering department at the University of Oxford. Prior to this, I worked on Bayesian nonparametrics and am in the machine learning community. And I've sort of been coming in and out, working on my talk, listening. I read about 40% of the conference proceedings, so on and so forth. And I have to say that it's utterly bewildering and kind of a little bit scary to stand in front of you and talk to you, because A, it's a big honor, and B, because we're kind of working on the same thing but use remarkably different language to talk about things. So I realized as I was working on my talk, most of my time has been spent trying somehow to figure out how to maybe use some of your words to try to talk about my work such that there's some information transfer. I'll probably fail. But just at the back of your head, think that AI, that's the big goal. That's what I'm working towards. That's what some of us in this field of machine learning are working towards. Certainly, most of us in probabilistic programming are working towards that. We just use very different language and different tools. So, great. Speaking of tools, you've all seen this slide since I've been flipping back and forth. There's an English expression which sounds like it could have been a German expression before it became an English expression. I don't know if you've heard this or not, but it's said that when you've got a hammer, everything starts looking like a nail. All right? Okay? Probabilistic programming is a lot like that. Probabilistic programming is an amazingly powerful hammer, and you can look at lots and lots and lots of different things, and they all start looking like nails. Okay? So that's sort of the promise of probabilistic programming. But actually, recently, some interesting things have started to come out of the probabilistic programming literature, at least some things are starting to be done and starting to be practical using probabilistic programming systems that might surprise you if you haven't seen them. One is that probabilistic programming makes it possible to take the historical notion of inverse graphics seriously. So perception as inverse graphics. Most recently and most successfully over here, if you haven't seen the picture paper, I highly recommend you take a look at it. They use probabilistic programming inference to invert a generative model that constrained a procedural scene generator, here of meshes and faces, with lighting and so on and so forth, a renderer, and a connectionist feature extractor for computing likelihood-free constraints. Okay? So they can invert that. You give a picture, and it will figure out a mesh and a scene description of a person's face, all within a probabilistic programming language. Okay, that's cool. How many of you have seen this directed design work out of Stanford? It's also pretty cool. It's actually basically the same thing, but probabilistic programming can be used to direct in the Pixar or film direction sense procedural graphic scene generation. This is basically equivalent to the previous application of probabilistic programming. On the left, Stanford researchers wrote programs to produce stacked structures that are stable in the statics sense, and then they went off and they actually built them just to make sure, which is kind of cool. And yeah, wouldn't you know it, they are. And on the right, they used inference to find scene descriptions whose rendering matched some sort of procedural cue or some sort of directorial cue. So they want a tree that sort of looks like this. Some director put this in. They use a generative model, which is a procedure. Everybody know procedural graphics. It's like generating scenes by a program. They run the program forward to generate geometry, and they constrain the program to look like the target, or there's a spaceship and you would like to have some collection of simple polygons, as few as possible, minimum description length, that look as much like the target as possible. Okay, so you can derive this design process via probabilistic programming and inference in probabilistic programs. Just as a sort of a fun little thing, this is beginning to be relatively serious. How many people know Pat Hanrahan, or the name? Cool. He was just recently listed as, well, he was one of the co-founders of Pixar, and most recently listed in the Wall Street Journal as being the only billionaire faculty member in the world. Okay, so we all will get there eventually. or not. Okay, so MIT and Stanford have the right idea. As usual, they produce lots of pretty pictures, and they sort of make a compelling story. Something that might be a little nearer and dearer to your heart is something like probabilistic program induction, which is another thing that starts to look like a nail when you have a probabilistic programming system. So I had the pleasure of having in my group for the last couple of years a superstar student called Yura Perov, who's attended this conference, and probably the reason why I'm here. So in my group, we've used probabilistic programming inference to do program induction where the programs we seek to learn are themselves probabilistic programs. So, oops, there should be a way to make video happen here. Oh, that would be really frustrating if that were the case. Okay, hopefully the other videos will work. So here, this is a generative model over, that's very, very frustrating. Let me see if this will actually go. Okay, no videos. Ask me later. Here is a probabilistic program that embodies basically an adapter grammar for generating source code, which is itself a sampler, source code that is a generative model itself. And then we can use a probabilistic programming system to train it to target a particular distribution. So given a declarative distribution of, say, for instance, a declarative mathematical description of some distribution, we can go off and learn blocks of code that, when run, generate samples according to the distribution of interest. Another piece of work that's recently come out of my group is that we figured out how to formulate policy learning in the form of probabilistic programming inference. So this policy learning in the classic policy learning in POMDP sense. So here I show 4 different probabilities of route taking for 4 instances of the Canadian traveler problem. How many know the Canadian traveler problem? See, this is what I mean. Totally different language and all. It's amazing. Okay. So, which is a classical partially observable Markov decision process in which you try to minimize the distance traveled from green to red, but only when trying to go down a road, you might find that it's been blocked by snow, requiring you to backtrack. Okay, so this is worse than the traveling salesman problem, because you go and then you get blocked and so on and so forth. So the inferred next node selection probabilities here are the parameters of a probabilistic policy expressed in the form of a program, which is itself a depth first search with stochastic next node selection. Okay, so we're going to learn the parameters of a stochastic program, which is itself a policy, which is itself a program. Okay, great. Okay, so we can actually do this stuff now, which is kind of cool. Okay. By the way, I know that there's supposed to be discussion at the end, but I find that kind of boring because, and I find it very difficult because I can't remember my questions till the end. So if you want to interact, please do. It would be way more fun for everyone if you did. So ask questions, make comments, yell at me, whatever. Okay. Great. So, given that I've just described a bunch of nails that you can hit with probabilistic programming hammer, we can do all of that. What is it? And I know that Noah came here last year and gave a talk, but I'm guessing that it won't hurt to sort of give the probabilistic programming spiel again. So, let me lay out the landscape for you, at least the way I see it. So, probabilistic programming is an emerging field. It sits sort of in the intersection of machine learning, statistics, programming languages, so on and so forth. One way of saying it is probabilistic programming is about using programming languages techniques to abstract inference algorithms from statistics and machine learning such that they automatically and correctly apply to the broadest possible set of reasoning applications. Okay? Great. That doesn't really mean much. Every talk has to have a Venn diagram. There's my Venn diagram. There may be another one later. Okay. Every talk also has to have conceptual pictures, and here are mine. But this one actually is kind of serious, and if you don't get probabilistic programming, there's been some excellent talks on it here, but I would encourage this community. You guys are like the ideal community for using this tool, and if I can convince you to understand or get you to understand the probabilistic programming conceptualization, or the way we think about problems, the way such that you can turn your problem into a nail, then this is great. There are existing systems. I want you to come on board. Okay, wonderful. But here's the conceptualization. In computer science, roughly construed, we write programs, or we write expressions which correspond to functions, and we evaluate them given arguments or parameters to produce some output. Okay? So in general, we're given programs, and we're given their parameters, and we evaluate the program expression to produce some output which is unknown at the start. Okay? Like, we all know this story. It's trivial, right? Statistics is really different, right? And I do statistical inference, and maybe this story is less familiar to some of you, but if you look at the world this way, this is a coherent way of looking at and modeling the world. So what it looks like is you write down some sort of generative model of the world, which, given some prior or some sort of parameterization of your ideas about what kind of worlds are possible, says something about the likelihood of observations y. Okay? So here are some observations. These are observable quantities in the world. Here's your generative model of the world. Okay? Now, what we get in statistics is we get this output, and we have the generative model, and the task is to figure out or characterize something about the x's that could have given rise to the observed y's. Right? I will typically talk about describing the distribution over the x's that could have given rise to the observed world, but we saw some talks yesterday about optimizing, trying to figure out the x that could best explain the y's. There's some problems with compositionality if you do that, but I digress. Okay, too much time on this slide. Let's get to the point. Probabilistic programming is the computer science generalization of statistical inference, period. Okay? So what you have is a program is your generative model. Okay? That's really deeply important. It is whatever program you can write down, that is your generative model. Okay? Now that program is going to be imbued with some special stuff, and we'll get to it in just a second, but it's just a program. That program is generative all the way down to whatever you observe. So there are some observations. You're given both of these, and what's different about probabilistic programming as opposed to traditional programming is that what you don't get are the parameters, the inputs to the program, the arguments to the program, and what you'd like to do is figure out the distribution over, or settings of parameters to the program that when run through could have generated the observations, okay? And this fully generalizes the picture over here and expands the expressivity class of the kind of models that can be written down and operated upon. In general, when I use the word inference, I'm going to be talking about turning these arrows around and figuring out what the deal is with the parameters, the latent variables, whatever you want to call them, given the observations, trying to invert some sort of generative model expressed as a program. Okay, great. So now an operative definition. Probabilistic programs, the text, the thing that you would actually write, are usual functional or imperative programs with two added constructs. One is quite regular, normal. It's the ability to draw values at random from distributions, rand, randin, so on and so forth. But most importantly, the ability to condition values of variables in the program via observations. And I hate to say it, but Andy, who's a good friend of mine, got it right and deserves to have written the paper entitled Probabilistic Programming, even though it kind of annoys me that such a paper exists. So this is right. That's what probabilistic programming is about. Wonderful. Okay. What are the goals of the field? What do we get? Well, we get to be able to see lots and lots of things as nails. One of the goals is to increase programmer productivity. So this is an example analysis written in, the output of an example analysis written in one of our probabilistic programming languages, and it's almost meaningless except for the following. Let me explain what's going on here. So we would like to be able to write down really complicated models because we think really complicated models are necessary to solve AI, blah, 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 okay? It's difficult to do so because, A, you always have to rewrite inference. Okay, so we'd like to amortize inference out, get rid of inference. But also the expressivity class of say, for instance, the language of directed graphical models is too restrictive. Okay? And programming in them, in traditional programming languages, is too inefficient anyway. So what we have here is a bunch of very complicated models that I would love, each one of these would be a super long, super interesting talk for this community. This is probabilistic deterministic infinite automata. It infers automata, their structure, in a completely unsupervised fashion from observational data. Awesome. This thing right here, it doesn't really matter. The point is, these really awesome models, which nobody here knows about, take enormous amounts of time and effort in coding in order to write them down and perform inference in them in traditional programming languages. But when you stick them in a probabilistic programming system, the languages are sufficiently expressive to result in a massive reduction in the number of lines of code required to encode the same model. Okay? So individuals are going to be much more efficient. And just to explain everything on the slide, this little inset figure here is a Bayes factor ratio of evidence computation done in Anglican to ask the question whether or not there's a logarithmic or linear reduction given these 1, 2, 3, 4, 5 data points in the number of lines of code. Who cares? I don't really believe it, but the point is that you can do these kinds of analyses very straightforwardly in a probabilistic programming system that exists today. Okay. Moreover, and this is really the hammer, so the language expressivity is important. We want to be able to encode complex, interesting generative models in higher order, Turing-complete, blah, 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 programming languages. But really the win comes from commodifying inference. That's the hammer. Inference is the hammer, okay? And how do we do that? Well, whatever our models are, and we all have different ideas about what the models should be, provided that we use a programming language representation as an abstraction layer, and we design it correctly, and we understand what's going on, then we can use, then that can separate our modeling environment from our inference engines, and we get all the sort of standard benefits that come from programming language abstraction. So models can be specified as programs, general purpose inference can be deployed to perform inference in the models specified in the said language. So if you work on inference, which I would say is what all of us should really work on, then it will apply to every model that's written in that language. And if you're particularly interested in working on models instead of caring about inference, that's the hard part, then you can write your models and try out lots of different inference algorithms straight away just by having coded them in a language that has inference as a commodity. Okay? It turns out, actually, that probabilistic programming has a very rich literature. It did not start with Church. There are many, many, many languages before Church, starting way back with the original sort of stochastic simulation language called Simula. Prolog fits in the family of programming languages systems. Now, I don't know everything about every one of these languages. It's almost impossible to, actually as an individual explore this space. I've only personally written in probably 8 or 9 of these languages. But let me try to do the following, just to give you a sense of what's going on. The languages in statistics and early machine learning are very restrictive languages in the sense that they only support bounded recursion. Some people would say they're not Turing complete, but of course no language is Turing complete. It's only finite Turing complete because of the computers they run on, whatever. Over here, these really, they don't really support recursion. They support looping with finite bounds, finite and deterministic bounds. And the reason being that what you'd like to do is you'd like to interpret your probabilistic program as a graphical model such that you can run specialized inference algorithms on the graphical model. So in other words, you're going to unroll the program as a DAG, basically, and then run, existing inference algorithms on that resulting model or induced model. I would say that there are probably 2 instances in here. If you're unfamiliar with them, you should definitely check them out. One is Stan. I was lucky enough to be at Columbia when they were first starting out with this and gave them some helpful suggestions. How many of you have heard of Stan? Ooh, that's bad. Okay. Great. So Stan says we're going to have finite models. Actually, that's maybe not quite exactly true, but generally speaking it is because their inference only works on them. We're going to have finite models whose parameters are all differentiable, or where the joint distribution is differentiable with respect to all the parameters. Then we're going to run Hamiltonian Monte Carlo. So we have a specialized model, which means we can use specialized inference, which means that we can do really awesome things pretty fast. Okay? So that's widely used in the financial industry and in statistics for actually doing proper statistics. How about infer.net? Oof, okay, all right. There are these tools out here, guys. You gotta check them out. They're pretty awesome. Okay, infer.net induces a factor graph, which means that you can run expectation propagation on it. It's the thing that selects your opponent on Xbox Live by running TrueSkill. So this scales to factor graphs with millions and hundreds of millions of nodes, and inference is wicked fast. Again, because the expressivity class of the language is restricted, and you can run special purpose inference algorithms on the resulting model. Great, so if you can plug your program in there, I don't think we're going to get AI in here, but they're very practical. On the other side, programming languages, people like to be able to prove formal semantics and make very formal statements about what their programs do, which means that they can't deal with continuous variables, basically. So most of the early AI people actually sort of worked very closely with the PL people. So there's a historical emphasis on exact inference and recursive conditioning and these kinds of exact inference algorithms over here. But basically, discrete random variables only. Great. So what I'll be talking about is this new class of programming languages, which although Church is definitely not the first, Church opened our eyes to a fair degree and said, oh, wait a second, actually we can do some stuff. Now, I should be very careful to point out here, and I think there's a little bit of confusion about this. Church, the paper, was a paper about the language. There was no inference in Church, effectively. Church was originally a rejection sampling, was based on rejection sampling, which doesn't work, period. But very, very recently, we figured out how to do inference that isn't rejection sampling, that actually works on relatively interesting sized problems. Okay? We haven't solved AI, obviously, otherwise we wouldn't be sitting here. But we've made a big step change recently in the last couple of years. Okay? So my group is responsible for Anglican and Probabilistic C and Probabilistic ML and Probabilistic Haskell and Probabilistic Scheme. The Stanford people, there is no Church anymore, just so you know. The Stanford people have a language called Web People, Web Probabilistic Programming Language, which actually we've sort of Anglican and so those are the Church people that went to Web People. We made some nice inference algorithms. They use our inference algorithms. Cool. Venture and Anglican basically happened at the same time, and Vikash and I have worked together pretty extensively on stuff, mostly on the design of languages, although Anglican syntax has diverged from Venture's. Okay, great. On to a language. Anglican. Please check it out. You can do lots of interesting stuff with it. Okay? It's a higher order pure functional language. It is compiled, not interpreted. It's relative to interpreted languages, much faster. Okay? We compile an Anglican program through a continuation passing style transformation to native Cloture code, which Cloture is just-in-time compiled to JVM bytecode. Great. Which you can take it or leave it. This gives us complete JVM family language interoperability, so anything that's ever been written in Java you can use in Anglican because Anglican is Cloture and Cloture is Java is the JVM. Great. Okay. Web People and Anglican. It's hard to say who introduced this first. I think we've got to it first publicly, but it doesn't really matter. It's the same thing. Anglican has first-class distributions. All the talks you've seen here do not. It's very important for inference that you have this, and I highly recommend that you pay attention to this. We've found it very useful. And here's the real kicker. Already, and this is and counting, 15 plus composable inference engines, Sequential Monte Carlo, the particle cascade. How many of you have heard of the particle cascade? Cool. Okay, awesome. So that came out of our group. which is sort of a SMC on super hypersteroids, particle Markov chain Monte Carlo, which is where we got our start in Anglican, including particle-independent Metropolis Hastings, particle Gibbs ancestral sampling, adaptive LMH, we have simulated annealing, we have search-based methods, so on and so forth. There's tons and tons of inference algorithms that you can just use, okay? I should also point out that if you want to work on inference, which is really where it's at, as far as I'm concerned, all of these inference algorithms are about 50 lines of code. It's very hard 50 lines of code to write. It's incredibly hard to write, but it's about 50 lines of code. And from start to finish, when I get a student and they write their first inference algorithm, it takes just a couple of months to understand everything. Cool. Anglican is open source. And I'll just point this out there. There is a website. It's a little bit behind where we are. Where you should really look are here in Bitbucket ProbProg. Anglican is the core of the language. Everything is there. It's completely open. GPLv3. If you want to program in Anglican, you don't need the core. You just need a user repository, so you can pull that down and actually start programming like that. And depending on interest, I just spent the last 2 weeks teaching the next generation of machine learning researchers about Anglican and how to program in probabilistic programming languages in general. And there's a tutorial here for the Machine Learning Summer School 2015 that takes about 4 hours to go through. And since I'm in town, and since I'm here, and whatever, if there's time or there's interest, I'd be very happy to sort of go through that with people. What does Anglican look like? Well, and what can it be used for? Well, it can basically do all the things that we talked about, albeit with varying degrees of efficiency. But what does the language look like, and what can we do? Let's start with the very, very easiest problem, traditional statistical inference problem. So we can sort of get you thinking about generative models and inversion of generative models, and what it looks like when you have inversion as a hammer that you can hit things with, inference as a hammer. So here we go. I don't know if you can see this in the back. That's as big as I can make it in order to see it. If you can't, please come forward or squint. Or I'll show you the slides afterwards. So here we have a thing called a def query, which is like a def function or def in or something like that. It's a Lisp. How many of you are functional programmers or have programmed in functional languages? All right, now we found my home. Okay. I don't have to worry about parentheses. Okay, how many of you have programmed in Clojure? Holy jingle jangles, great, okay. That's the largest number I've ever seen in any audience, so okay, all right. Now if I can convince you to think generatively, we'll be on the same team. Okay. So let's do traditional Bayesian statistics. So here's a model. A model is actually, it specifies a posterior distribution conditioned on some data. The data is the parameter to this model. Let's have a let block. We're going to have a little some local bindings here. If you're a Lisp programmer, just interpret all the square brackets as parentheses, basically. So mu is going to be a sample from a normal distribution with mean 1, standard deviation square root 5. Sigma is going to be a constant value. And we're going to do something funny here. We're going to map a function which calls observe with a normal distribution with mean mu, which is stochastic, standard deviation sigma. And this function takes a single argument, x, and we're going to map this function over the data. So in other words, this is basically like plate notation for a graphical model, if you're familiar with this, but really what we're saying is we're going to observe all of the data items in this set, and those data items come from this probabilistic model where mu is drawn from normal, and it's unknown, but we're going to observe a bunch of y's, and we want to know what the value of mu is. So we're going to predict this. So that is not Clojure, that's Anglican. You won't be able to tell the difference syntactically if you're a Clojure programmer. They're designed to be basically exactly the same. However, they're different languages. Great. Okay, so that's the simplest program you can write. What do you do with it? Well, a posterior distribution, I said, is a conditional distribution parameterized by a data set. Well, there's a data set. It's just a vector of values corresponding to assigning the values in this model. I already said it. I'll say it again. A posterior distribution is a conditional given a model, and a means of characterizing the conditional distribution here, we'll use P-Gibbs. This could be any one of 15 different inference algorithms, and they're all composable. Great. A conditional specified by the model, given a particular data set, that's the posterior distribution. Great. And then we can characterize the posterior distribution by, for instance, sampling from it repeatedly which in this particular case, because this model happens to have an analytic closed form solution, we see that the posterior distribution induced by this particular program very, very closely matches, and in fact will converge in the standard Monte Carlo sense to the true posterior distribution. Okay? If the videos don't work on the next one, I'm going to be really pissed. Okay? Okay, good. Cool. All right, so that's the simplest program. Let me try to stretch your mind just a little bit and give you a sense of how, when you have inference as a hammer, or probabilistic programming as a hammer, you can start to think about different kinds of models and solving them in a different kind of way. Okay, so here's the task. This was actually in the summer school. I can run either of these programs for you. They run very, very quickly. It's really not a problem. So let's do mechanism design. Okay. This is a world. It's a 2D world for ease of display and pedagogy. The world is simulated by the JBox 2D simulator. Anybody know that? Anybody played Angry Birds? Oh, admit it. Everyone here has played Angry Birds. Even I've played Angry Birds. We all have to do something when we're on the toilet. I don't know. So that physics simulator is the physics simulator in Angry Birds. Okay. So great. What are we going to do? We're going to do mechanism design, and we have a goal. We want to put 20% of the balls that fall from this platform into that box. Okay? All right. And probabilistic programming. Once you get used to it, it's a weird, weird hammer. You can hit lots of things with it. Okay. So let's define a query called arrange bumpers. We're interested in the posterior distribution over worlds that will cause 20% on average of the balls to go in that bucket. So world creates a world. That's some piece of code that creates this world. End world simulates the world. It runs the physics simulator really, really, really fast. Faster than real time. That's real time is just for display purposes. You can simulate faster than real time, obviously. This is just a way of getting the information about the balls at the end of the world. And then we can ask how many balls are in the box. Great. So, and then we predict the number of the balls, how many balls in the box, and where the bumper positions are. So, so how would we solve this? Well, one way to solve this is simply to just stochastically generate in the same sort of way that you do in the procedural graphics case or in the taking inverse graphics seriously case. Let's just make up worlds. Okay. Cool. So. Great. So we have a generative model, so we're going to have some number of bumpers. Go back, it's fun when the graphics are going. We have some number of bumpers. Let's just say there are plus on 20 of them. I don't know. Great. And then there are some position distributions. So we'll say that the y distribution is between 0 and 10, and the x distribution is between -5 and 14. And let's repeatedly, number of bumpers, call a function which creates a vector by sampling from each of the distributions. Great. So those are the bumper positions. And now we just run the simulator with those, and you'll notice that we generate worlds. And this is the prior that we have specified in terms of a probabilistic program. Okay? Anybody have a sense of how we might use the probabilistic programming hammer of inference to solve this problem now? Suggestions? Got your head screwed on? We're not going to move the bumpers. We're going to make the probabilistic programming system move the bumpers. Yes, of course, you want to move the bumpers, but we need to observe something. We need to constrain the execution traces of this program to do what we want them to, yeah? Brilliant. Yes, absolutely. So let's do that. Okay, awesome. There's design. We have an observation distribution. We say we want 2 out of 10. I'm sorry, 2 out of 10 is whatever. I want 2 out of 10 with relatively high probability to end up. So I'm just going to observe. I'm going to say, you know what? I'm only interested in worlds in which 2 out of 10 of the balls, on average, show up in the bucket. Cool. Okay. 2, 3, 4, fine. They're all okay. Roughly 20%. Should I do that again? It's kind of fun to watch. And I can say that you would have a very difficult time actually coming up with one of these worlds because you see how they work. This is like some weird system that like learns how to balance a ball such that one in every 5 goes in the bucket, and who the hell knows what came, really? Really? Okay. So you'd have a hard time actually doing this design task. It would take you quite a long time to figure it out. And I think I think at this point I probably need to do this in order to convince you that this isn't just some sort of dog and pony show that doesn't actually work or do anything. So this is always a scary bit here. So we have this closure. It has some nice stuff. Whoa, that's not what I want. Pardon me. You can't see anything that I'm doing. I'm guessing if I do that, you'll be able to see it. Ah, no. Come on. All right, I'm not going to. Aha, okay, cool. So there's what's it called when you have an IPython notebook type thing where you have comments and text interleaved with code? There's a particular kind of programming that's called? Literate. Okay, cool. Yeah, so Clojure via Gorilla REPL supports literate programming in the browser. Okay, so we didn't do any of that. Great, but we support it. So here we go. This is part of the machine learning summer school tutorial. There's the code that I just showed you. Great. So that specifies a query. This runs inference quickly. I'm not plugged in, so my machine's a little bit slower than usual. And this is the scary part now. Okay. Come on. Come on. There we go. Yeah. Okay. So it's and we can run this 10 different times or 100 different times. You're going to get completely different samples from the posterior distribution. And I see your question, but I'm going to drink some water while you're asking it. Just because that's entertaining, let me see if I can figure out how to close that. Let's be really crazy and actually run inference again. Of course, if you know anything about Monte Carlo inference, every time I do this, I'm like flipping a flaming sword of death over my head because there's a very good chance that it won't actually converge, and then I'll look silly. And I'd have to explain it. But there's a different world. Let's see if that one works. Oh, it's looking promising. So stressful. Okay, there was a question back there.
Well, what's supplying the input randomness? Because if it was deterministic, then every ball would follow the same exact track.
It is a deterministic simulator, and that's what makes this kind of an interesting problem and sort of complicated to think about, right? So what the inference algorithm has to do, and God knows how it does this. Actually, I know how it does it, but it's kind of magical, right? It is a deterministic simulator, but this thing has to figure out how to bounce balls such that they interact, such that in a deterministic simulator, 20% of them go into the bucket on average. So there's no stochasticity in the balls, there's no stochasticity in the simulator, but there is stochasticity in where you put these things. And the balls can interact, and they can have deterministic oscillations that mean that some percentage of them get kicked out, and some percentage go in. You've seen it happen, in multiple cases. So, yeah. Nope. So, in both a good way and a bad way, the inference that we do is actually really simple. Okay? It's general purpose inference. We know nothing about inverse kinematics. We know nothing about the physics simulator. We know nothing about that. But we do know how to do inference over the traces of probabilistic programs. And we do that very efficiently. Okay? So there is some kind of general purpose inference. Whether or not it's the right general purpose inference, I don't know. But the point of showing this is to show that we actually can do inference over relatively interesting generative models expressed as programs relatively quickly, even though we do stupid inference. But there's a question here, but you have a follow-up, yeah?
Okay, so can you rephrase my question? You don't have JBox2D implemented as a probabilistic program?
No, it's a black box. Somebody gave us JBox2D. Yeah, of course. That's the whole point of at some point, if there's time remaining, I will make a statement like, please don't write your own probabilistic programming languages. And please don't make special probabilistic programming languages. You can make every language a probabilistic programming language, and in so doing, you get to use everything that everybody's ever written before, like JBox 2D.
In order to condition the parameters on the observations,
Yep.
it's a full joint distribution,
Yeah.
right?
Yeah.
Parameters and observations.
Uh-huh.
Do we have to specify them, or do we have some default assumption about this full joint distribution?
The joint distribution is, I'll explain what the joint this is an excellent question, okay? So I don't know if everybody could hear that, but the question, to paraphrase, is what the hell is the joint distribution if you're going to be doing inference? Is that a reasonable, okay. I think the very next thing that I'm going to talk about is what inference is over. Okay? Great. Any more questions here? Anybody finding this vaguely entertaining? Compelling? Were those questions? That was really scary right there, because like 50 hands went up. Okay, great. Okay. So I take it, having read a bunch of stuff, that this isn't necessarily the, like, how many of you would call yourself Bayesians? Oh, why aren't you guys in the proceedings? I don't understand. Okay. All right. So what we're doing is, okay, so great. I don't have to explain this too much, but I'm just going to make a couple of points. So what we're doing, this is the hammer, inference, okay? So we have this setup where we have some hypothesis or hypothesis space. We have some latent variables in the world, and we have some observables here, okay? Quantities of interest, and this is sort of the turning things around. So we have a generative model given a hypothesis and latent variables, which generates observables. We have some prior given a hypothesis on the latent states of the world. From that, we use inference to characterize the posterior distribution of the latent variables given the observations and the hidden states of the world. And while in the process of performing inference, in the process of doing this inversion, we also compute as a side effect, basically, something about the evidence for the observations given our hypothesis. And this is how we can do model comparison and these sorts of things. And of course, the evidence is this absolutely hideous integral over the space of all possible latent configurations or random variables in the world. Okay. I will point out that this distinction between H and Z is Z. I'm American, but I live in the UK. It's complicated. H and Z is artificial. But I put it in here only because there's a lot of people who care about MDL kind of stuff in this room. And I'd just like to point out that, that in this framework, you get an automatic complexity regularization in the form of Bayesian Occam's razor. Now, this is basically a shout out to some of my friends, if you know David Mackay or Ian Murray and Zubin Garamani. They have a couple of papers on this where using the evidence and this formal framework, the posterior distribution over hypotheses, i.e. how good a hypothesis is related to the evidence and the prior on your hypotheses, okay? And there's an automatic win for simple models. So simple models must concentrate their mass on small parts of the data space, which means that if you have typical data, you encounter typical data, then simple models will dominate complex models. Okay? That's a lot of verbiage, and it would take a semester-long course to really explain this one very simple diagram and get it to go in if it's not in your head already. But number one, read this bottom paper, Ian Murray, Zubin Garamani, a note on the evidence of Bayesian Occam's razor. It's about 4 pages long. It takes about 6 months to understand. In my case, it took about 10 years to understand, but okay, a little slower than the rest of us. What does this really mean? If you're doing program induction, great, cool. If you write, I'm going to try to concretize this a little bit. If you write a generative model for your programs and your hypothesis space is a prior over programs, then you have an implicit geometric prior on the length of the program, which means that when you turn the Bayesian crank, you're going to prefer short programs that explain typical data. Okay? Cool. Like I said in words, this distinction between Z and H is totally unnecessary. They're all latent variables, and you can be fully generative if you so choose. And probabilistic programming takes generative modeling very seriously. It's fully generative, okay? So that's that's it. There's some latent variables in there, there are some observed variables, and we'd like to uncover the latent variables given the observed variables, and we'd like to do this automatically through inference. Just to sort of name what these x's and y's are, if we're doing program induction, then x is the space of program source code, and p of x is some sort of generative model for program source code. How many of you know adapter grammars? Okay, cool. There's a nice framework for generatively, for generating S expressions, for instance. That's what we use in our work. So a lot of machine learning, a lot of interesting machine learning comes down to writing down an interesting p of x for all of these classes of problems. So x program source code, y program output, invert, figure out what program source code or the distribution over program sources that could give rise to output. Magic Haskell expressed as inference. Cool. Scene description as the space of mesh models. Y's are the rendered images. X's is the space of policies expressed as programs. Y's are the rewards accumulated by acting according to that policy. X's are the worlds in sort of the bouncing balls case. Y's are the simulator output, what JBox2D says the end of the world will look like. And in the case that I took out of the talk because I don't think I have time for it, you might, for instance, generate automata or actual circuits. You can write down generative models for that and then expose them to sequences and infer the structure and function of automata directly. Okay, so this framework's pretty large, and you really, in certain, I mean, it's very difficult to think about writing down scene descriptors and rendering them to images without the power of a programming language, or worlds and simulators without the power of programming languages, or so on and so forth. So having the probabilistic programming language gives you two things. One, the ability to write down models, p of x for these things, priors. That's good. But also this magic ability to invert y into x. So I'm finally getting to sort of an answer to your question. How does it work? What the heck is this about? Okay. So the gist. This is the pedagogical component. And I keep that, any interesting keynote has a very small amount of pedagogy and a large amount of selling. I apologize for that. I prefer pedagogy. So ask questions here. I can actually answer them, okay? So the gist. Let's explore as many traces as possible intelligently. This is just terrible. Okay, a trace, I'll explain what a trace is in just a second. But for now, each trace contains, but doesn't entirely consist of, all random choices made during the execution of a generative model. Great. We will compute trace goodness in terms of some sort of joint probability as a side effect of running the program. And we're going to combine weighted traces probabilistically coherently such that the weights and the traces can be interpreted as a posterior distribution over traces. And then we're going to report a projection of the posterior over traces. And that's syntactically this predict statement, which takes parts of the environment and predicts their value under the posterior distribution over traces. Okay, so I have to tell you what a trace probability is and what a trace is sort of simultaneously. So I've chosen to tell you what a trace probability is first, and then we'll look at traces and we can go back and forth. And please, by all means, ask questions. Okay. So this is a little different. If you haven't read our work in particular, this formulation of the probability of a trace is actually equivalent to everything that came before, but it's a little bit more notationally explicit so you can see what's going on. So I should also point out just straight away, I notice I've started indexing things by y's. This is just big Y, and that's just big X, and it's the same as on that slide. Okay, now we're going to allow there to be some additional structure. You could either think of removing all of this, that's the original thing, or just lumping all of these together and all of these together, and it's exactly the same framework, okay? So, great. Let's assume that there are n observations in our program. Big N of them, okay? It's an assumption that can be fixed, but for pedagogical purposes, that makes sense. We're going to call every observation yn for y1 to big N, okay? And we're going to have sets of internal random choices made during the execution of the program, and those sets are bold xn. Okay, so those are going to be the sample statements encountered during the execution of the program. Okay? So executing the program we'll call simulating or running the program forward or something like that. That's going to be drawing sets of random variables, in other words, running the program and executing the sample statements as the program runs forward. That's this F. Okay? And we're going to impose weights, or we're going to compute the goodness of every execution trace by executing observe statements where the observed quantity is this yn, and it's conditionally dependent on the generative model as it's run till that point. Okay? So we'll say the probability of a trace, define it to be the product of all of the observed statements, the log likelihood or the likelihood of the observed quantity yn given the sequence of environments up till that point, times the probability of extending the sequence of environments as is required in order to compute the observed statements. Okay? When I say extending the environment, does that make sense? Enough of your programming languages people that makes sense? Okay, great. So this formulation of the probability of a trace looks like this. So here's the sequence of environments, and here are the observations. Okay? So this intentionally is written to look like a state space model or a Markov model, which it is, kind of. Notice there are these little gray arrows here, and there are little gray arrows down here. I'll explain both in just a second, but let me go down here first and say that bold X, the set of random variables, is all of the sample statements encountered on the execution path until the nth observation statement. Okay, so this is X1, this is X2, so on and so forth. Probabilistic programming languages are capable of expressing complete factorizations of joints. In other words, all of these arrows can be dark. It's quite easy. The absence of these arrows corresponds to scoping restrictions and variable usage in whatever generative model you write down, right? If some variable here loses scope when you're in this program segment, then clearly there can't be an arrow from here to here because you can't see the variable, okay? So it's very expressive. You can write a full, a complete factorization of any joint, okay? So what's a trace? So let's look at a little program fragment. I apologize for those of you in the back of the room. You probably can't see the bottom bit, but it's sufficient to understand what's going on up here and listen to me while I wave my hands about this. So a trace, I think you're starting to get it, is the sequence of bindings and environments that are built as the program executes. So here's a little program fragment. Let x11 be 3, so that's a deterministic assignment. And then let x12 be a sample from a discrete distribution over the range 0 to x11. Okay? So now a trace is a particular choice of that variable value. The set of all traces is sort of, I think of it as the many worlds interpretation of a probabilistic program, is the set of all traces that could result from all possible choices for that particular random primitive. Okay? And then, if not equal x12, 1, as in, i.e., not in this path, in this trace, but instead in the others, then assign x21 the value of x12 plus 7, so that's another deterministic operation. We've got a new binding. And then, from that point forward, sample Poisson x21. Okay? So a trace will make a particular choice for the value of this random variable, but in fact now we have countable branching at this point, and the program set of all possible execution traces is infinite straight away. Yeah? Let me answer your first question with the next slide, and then when I don't answer it sufficiently in the next 2 or 3 slides, then I'll try to parse the question fully. So there's no observed statement here. That's the first thing, right? So, like, what's going on? So this is in a non-deterministic environment. This is a problem, right? Okay. So what if I stick an observed statement in here which says, I observe Gaussian x21 is 7 with very small standard deviation? Okay. So that's saying, this is the slice of the program where the choice of the value of x21 is made. Okay? So if there's an observed statement in here on that particular variable, and it says it's 7 with pretty high probability, then while we're computing, we're going to compute a side effect. We're going to compute the probability of this observation, this value here, under this distribution. Distribution objects are first class, and all observations must be noisy for lots of reasons. Then the top blue trace automatically will be much, much preferred to this trace. Okay? Now, in the practically unachievable but theoretical case, if we could actually enumerate all possible paths and assign probability values to every possible trace according to these kinds of statements, then we're done. Because we've enumerated all possible worlds and we've assigned values to all of them under the observation model. Okay? Of course, we can't do that, right? So the question is, how do we do that efficiently, right? Okay, and that's where sort of the breakthrough in inference occurred, starting basically with Anglican and now integrated into Web People and so on and so forth. Okay, how many know sequential Monte Carlo? Particle filtering. Okay, a little bit, cool. Okay. Super fast pictorial review for those who don't. Imagine a physical system in which you get measurements of something, some process that's evolving in space or time, or there's some rocket going somewhere and you get radar measurements of it or something like that, and you want to track it. So one thing that you can do is run a simulator forward, and then condition your simulator based on the likelihood of the particular observation you get given the simulator up till that point. Okay? So simulations we call particles. We're going to run them forward until they hit some observed boundary. We'll compute their likelihood under the observation model. They'll get weights. These are pictorially represented by the size of the circle here. They get weights, and then from that point forward, for various statistical distribution, sample from that distribution, and then weight the samples by the ratio, and that's a sample from the distribution you want. Words, I know. But you'll see it in 2 seconds here, which is to say, we can't sample from this thing because we don't know how to sample conditioned on y. But we can sample from this thing. It's very easy. We have a representation of this distribution in the form of this set of parallel executions, weighted set of parallel executions, and we know how to sample from this. How do we sample from this? Huh? Somebody said it. Just say it out loud, louder. Don't be shy. I heard you say it. You said the correct thing.
Run the simulation.
Yeah, run the simulator forward. Okay. So this is going to simulate forward. It's just going to run the program, making random choices. So that's this bit here. So now we can propose from this, and we want samples from this. But you can imagine if you believe important sampling, which I said. You want samples from this, you can propose from this, and you need to compute weights, and it's the ratio of P over Q, then the only thing that's left is this. And that's computable by design because that's an observed statement. Okay? So syntactically, this must be computable. Cool. Okay? Great. So now we have an important sampling kernel which allows us to move our executions from n-1 probabilistically coherently forward to n by, and this is very notationally compact, and this is the kind of crap that you have to deal with when you read papers from my group. I apologize for that. It's actually really simple, but notationally horrific. So in order to sample from Q, we need to run the program forward to the next observe. How do you do that? Well, we pick one of the previous traces from the weighted set according to its weight. So this ancestor is an indicator variable between 1 and L, picked according to the weight distribution there. And then we just run it forward by sampling from F. Okay? So that gives us an environment. It gives us a new sequence, an extended sequence of environments. Great. So that's the atom here. And then the new weight is just P over Q, which we can compute by the observation distribution. Okay? So that gives us this. So, and that basically completes the recursion. You start at the beginning, you run forward, you wait, resample, keep running, so on and so forth. Okay? And I'm actually not hiding that much. It really is basically that simple, okay? I should say the only thing is these things, of course, are computed as side effects. They're computed inside either the interpreter, if you use an interpreter, which you shouldn't because you don't need to, or inside the compiled executable as a side effect of running the main program, okay? So in essence, SMC, for probabilistic programming, works like this. You have multiple computation threads. Call them parallel processes, actually, because that's really what you want for memory reasons. Run the program forward, run to an observe, compute weights, preferentially kill some of the executions, continue forward, reweighting, okay? Run, wait, and people have pointed out that this wait means actually wait and compute weights, so both spellings of wait here in English. Fork, and I actually mean fork. I'll show you something in just a second that should make you laugh, okay? Fork and then run forward. Okay, so I can almost explain SMC almost, maybe, somewhat coherently in a short period of time. What we actually do just builds on that, and it's actually not that much more complicated, but mathematically it's much, much more sophisticated, but basically the same thing. SMC doesn't work, okay? And it doesn't work for the same reasons as is usual. Too few particles to explore the entire space. Choices made early in the execution trace because of the way reweighting and resampling works get fixed, and you can't mix out of those. You usually have poor estimates for choices made early in your simulator, and those are usually the choices you care about. And maybe more importantly, it's not iterable. Once you run SMC, at least naively it's not iterable, once you run SMC, you're done. You can't then run it again, and so on and so forth. That's not true anymore. And in some very, very important work that appeared in the Journal of the Royal Statistical Society, Series B in 2010, by Christophe Andreu, Arnaud Doucet, and Roman Holenstein, called Particle Markov Chain Monte Carlo. How many of you have heard of Particle Markov Chain Monte Carlo? Okay, this is the most significant advance in inference in the last 50 years, probably, okay? And it's extremely powerful, and we were lucky to be the first to say, hey, wait a second, this actually is compatible with probabilistic programming and means that we can actually do some things that we really want to do in probabilistic programming. So PMCMC, Particle Markov Chain Monte Carlo for probabilistic programming, is sort of the beginning of Anglican. We've gone quite a bit further since then, and it appears in a paper entitled A New Approach to Probabilistic Programming Inference. Makes the realization that PMCMC can be used for probabilistic programming inference, and PMCMC tells you how to iterate SMC in lots and lots of very interesting ways, which means that when you run SMC and you get some discrete approximation to the posterior distribution over traces, well, you can just do it again and combine those in various ways. Now, for those of you who care about genetic algorithms, actually a lot of what we look at here looks like probabilistically coherent Markov chain operators that look like genetic algorithms. You run an entire set forward, you run another entire set forward, you compare the fitness of the two, and then you reject or not. Or you keep one around and you compare based on a single Genghis Khan particle or something like that, okay? There are lots of ways to anthropomorphize these algorithms, but sequential Monte Carlo is a building block for other inference techniques. PIM8, particle-independent Metropolis Hastings, P-Gibbs, iterated conditional SMC, are really actually relatively simple, and they involve rerunning SMC and with various conditioning and reweighting each of the sets, okay? And what you get out of it is stuff that doesn't look that significant when you look at the plots. There's a win plot, but it's actually rather significant, which is to say that you get better inference per unit energy, okay? So whether you count by simulation or time, or somebody said, maybe we should be counting applies or evals or something like that, right? So for a very large variety of models, compared to the state of the art, which was lightweight Metropolis Hastings at the time, you get a factor of 5 without doing any parallel execution. So just in terms of like the number of applies, great. In terms of time, this is a single-threaded implementation, and we get roughly linear speed up if we just increase the number of execution threads, okay? So we've got an easy way to make this line go woo, way over here. It's called parallel processing. Okay, so Is that really 5 minutes, or is that 5 minutes with a little bit of time for questioning, or have I killed all the question time as well?
5 minutes and then 15 minutes for questions.
Okay, cool. So you're going to have to ask some questions because I really want to tell you a little bit more, and this is going to be awesome. So at PMC, I've been told 5 minutes, so I think this will make you, this next bit will make you laugh, and you'll probably want to ask some questions about it. Okay, so PMCMC and SMC methods only require being able to initialize, which means basically starting the program, forward simulate, which means being able to run the program and make random choices, and be able to compute these observations point-wise up to normalization. And that's really critical. That's the essence of probabilistic programming. If we could do this for everything, then we wouldn't have to do inference, nor would we have to do probabilistic programming. Great. Okay. Because it's so simple, I'm going to make a very controversial, and in fact, every keynote has to have an offensive statement. So here's my offensive statement. Okay, you ready? Stop making new probabilistic programming languages. You don't need to. Okay? It's an interesting pedagogical exercise, but it's a waste of time. Work on inference. Okay? The languages are sufficiently expressive, and we know how to sort of compile away the bits that don't correspond to inference. This is a solved problem now. Okay? And note that I actually say sort of, so it's not super offensive. But let me give you a sense of why, and it has to do with sort of the simplicity of inference and what you can do once you realize that you can do inference in this way. And please, please laugh, because this is really hilarious, okay? Not particularly deep. I don't know. It's fun. How many of you have seen Probabilistic C? Oh, cool. Okay, so good. All right. All right. So Probabilistic C also came out of my group. We wrote this in 2013 in a park in San Francisco, just for the fun of it. My student and I, Brooks. If you're looking for like a super freaking rock star student, this guy Brooks is amazing. I'm gonna hate losing him. He does all my work actually. So Probabilistic C is standard C with two new directives: observe and predict. It's compiled to parallel machine code by standard compiles. It relies on standard operating system functionality only. If you have a POSIX operating system, you can do Probabilistic C. Processes, forking, mutexes, shared memory. Compiled programs automatically do inference in the way that I was just talking about it. And when you run a program, it emits posterior examples of predicted quantities. This is what Probabilistic C looks like. If you don't like Cloture or something like that, I will say that writing new inference algorithms for Probabilistic C is a little more complicated than writing inference algorithms in Anglican, but you can do it. However, if you like C programming instead of functional programming, if you like imperative, blah, 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 you want to be close to the metal, this is the way to go. Here's a simple example program. This is exactly the same program that I showed you for the Gaussian unknown mean model. Okay? So here we include probabilistic.h. There's some main function. It's got a couple of variables, a variance, a normal random number generated mu, a normally distributed mu, and then two observations of 9 and 8 that are distributed according to a normal log probability, which we observe with this unknown mean and known variance. Then we predict, which is basically a report the posterior distribution of any string, whatever, or that doesn't really matter. We predict this value mu. When you run this program, it emits a stream of samples. So mean here, okay? And this has the same sort of Markov chain Monte Carlo convergence guarantees as before, okay? You don't believe me? I had Brooks make this video, a couple of videos. They're kind of fun. Hopefully these work. Okay, yeah, let me go back. Great. So here is a Markov model. So we're going to do three things that are kind of fun. We're going to do a Markov model, then we're going to do an HMM, and then we're going to do a Bayesian HMM where we learn the transition structure and dynamics of the hidden Markov model. I'm just going to blow past 2 minutes. Just cut me off at the legs when I really can't talk anymore. Unless you guys really, really want me to stop, in which case I'll stop. But let me do these really quick. Great. Here we are. Here's a transition matrix. It's k by k in this particular case. There's the initial state distribution. Here's a program. For n equals 0 less than n, if n is 0 at the beginning, pick from the initial state distribution. Otherwise, draw from the state distribution indexed by the previous state. So this is a standard generative model for a Markov chain. Here we go. Make, it's GCC. That makes the entire library and compiles the program and then runs it out through a Python script. And what you see is, of course, that any Markov chain is going to equilibrate to its equilibrium distribution as you run it forward. We know that's what Markov chains do. So there's the initial distribution, and then very quickly the Markov chain mixes. Great, okay? Cool. So how about we turn this into a hidden Markov model? What would we need? Well, we need to observe some quantities, some data. Okay, so we're going to turn the Markov model into an HMM by adding some data. We're going to impose some Gaussian distributed observation distributions for these things, and then if we're in the first state and beyond, then we're just going to observe normal log probability data given the state means for the state at time n that we've just generated here. Okay? So when we run this, compile the entire thing, run it, okay? There are the marginal probability estimates. Okay? Great. This is actually a little bit of a challenging problem. There's an inflection in the state space that's very difficult to get through, just to make sure that general purpose inference works. If you know hidden Markov modeling, then you would know straight away that you should just run forward, backward. So the ground truth marginals look like this. This is a proof of concept. Great, it works. Okay, so general purpose inference solves the problem, and it's only a factor of 100 slower or something like that. So you can't always do, and as soon as you write down interesting models, you can't do forward, backward. You can't do special case inference anymore. You have to do general purpose inference. And what happens if you don't know the transition matrix and you want to, say, for instance, do Bayesian HMMs or generate the transition matrix? Okay, great. Just declare it and generate it. So here we're just going to generate from a symmetric Dirichlet distribution the transition distribution for every state. Okay, compile it, run it, and inference. Okay? So why? Great. Implementation. It's easy. We macro rewrite your main, run your program in parallel many, many times, and use fork to we kill processes and we use fork to replicate memory state. On modern multiprocessor architectures, because pages don't get flushed anymore, page caches don't get flushed because you don't know where threads are going to be on multiprocessors, it turns out that this is actually really fast. Okay? But it also gives us the ability to do something really wild. And this is a paper that we're working on right now, entitled, provocatively, The Next 700 Probabilistic Programming Languages, which is a reference if you're a programming languages person. And this is work that basically Jeff Siskin did, but also Brooks and myself. If you happen to be, how many of you know Jeff? Heard of Jeff? Anybody heard of the Stalingrad scheme compiler? Stalin? Okay. All right. So Jeff wrote that. And if you happen to have a scheme compiler that compiles through C, and it supports foreign function interfaces, you get probabilistic scheme for free. So here's probabilistic scheme. Here's a likelihood, condition on the data. You've already seen this, and you predict something. This works just fine. In order to make probabilistic scheme, you take a scheme compiler, an existing C compiler, and probabilistic C. So long as you have a foreign function interface for your scheme, then I'm supposed to be done. I am almost done, actually. Then you're set. Okay, so we've got probabilistic scheme by compiling scheme through probabilistic C. There's probabilistic C. Here's a sum equals problem. We've seen something like this, right? A couple of random variables. We observe that their sum is 7. Then we predict their values. There are a large number of languages that compile through C and support foreign function interfaces. Obviously, C does because it's C. Scheme does. Standard ML does. Haskell does. So on and so forth. So all of these languages have probabilistic variance now. And they're pretty fast. And we can do sort of powerful general purpose inference in them. Okay, so the bubble up. Please work on inference. If you work on inference in probabilistic programming systems, it works for everything that you write in a probabilistic programming language. Lots and lots of models look like hammers when you've gotten this kind of environment. And I'd like to think, eventually, that there would be a bubble up to the kind of applications and the kind of thing that we all want to achieve. And I think, I'll skip over my other stuff. It's all about inference. There are a bunch of papers here that we can talk about. Parallelism, backwards passing, search, adaptation, novel proposals. That's where we spend all of our time. Please look at these. They're quite interesting. So I want to thank a bunch of people. I have a couple of fantastic postdocs. I just lost David to PayPal. Jan Willem van de Mint will be on the faculty market this year. He's spectacular. Yura just left me for Stanford. Brooks will be on the faculty market this year as well. He's ridiculous. Hong-Suk Yang, if you know any programming languages people, he's my programming language ace in the hole. These guys, you should read their papers. If you care about inference, they're where it's at. They're the modern Metropolis Hastings team, basically. Yi Te and Arnaud Doucet, and Jeff. If you're unaware, probabilistic programming just got a huge, maybe a couple of years ago, got a huge bump from DARPA. I have a bunch of that money, but there's a huge program to develop probabilistic programming languages. And Amazon and Microsoft have been very helpful to me as well. So thank you very much for your time. Hopefully this hasn't been too horribly boring, and I look forward to questions.
Okay, thank you. We have about 10 minutes for questions.
Yeah, in case the Monte Carlo simulation is not able to catch the observable, am I right to assume that you can artificially introduce any observables to guide the simulation? I mean, if you can actually enter into subroutine where you want to.
Okay, I think you asked two fantastically good questions simultaneously, at least in my way of hearing it. So let me see if I can unwrap them. One, there seems to be some concern about, in inference and general probabilistic programming systems, whether or not the generative model that you specify can match certain constraints. In other words, can you even find a satisfying solution to a specified constraint? Very carefully and for very reasoned theoretical reasons relating to work by Freer, Ackerman, and Roy related to the computability of conditional probability, our languages are designed such that all observes must be noisy. There are no hard constraints. You can't have them. You can get relatively close to that, so you can make inference harder by making your constraints harder to satisfy. But they can never not be satisfied by design. Okay, so and if you're unfamiliar with that body of work, I suspect many of you here could read it and understand it. I can't really read it or understand it except to know that you can't compute conditional probability unless, in the general case, unless your observations are noisy, unless there's noise in the system. Okay, so we took that seriously, and our languages are designed such that you must specify not hard constraints. That helps a lot. The second bit is really deep and very, very interesting, and I appreciate you bringing it up. The second bit is, if you have a simulator, a large number of nails that you might like to hit with the probabilistic programming hammer look like this. Simulate something for a really, really long time, and then observe at the very, very end. And we all know that pushing information back from observations all the way to the beginning of a simulator and so on and so forth is really the key. If you're doing reinforcement learning, you only get rewards at the end. It's very difficult to sort of propagate that back and make intelligent choices at the beginning. So yes, in these languages, and having formulated it in this way, we specifically have made it such that, and this is the procedural design stuff, this is actually exactly what they do. They go in and they say, okay, let's guide the computation by inserting observations early in the execution trace, as early as you possibly can. And the Stanford folks have been working on notions like heuristic factors, which say, in fact, let's use observations or constraints or factors or whatever to guide the computation towards something that we want.
Yeah, but do you mean that the algorithm infers those observables, or the human has to introduce them? To guide the simulation. I mean, it could be both, I guess.
The phrase infers the observables doesn't make sense to me.
Well, I mean, you have a variable, you can decompose it into other variables that.
Okay, let me. I understand what you're saying, but I'm going to answer it. I'm going to do the politician thing and answer the question that I want to answer. But it is actually the answer to your question. But okay, so the answer to your question is that there are programming languages people who are working on program transformations that automatically take block observations, decompose them, and move them as far forward as they possibly can. Okay? So that's very sophisticated program transformations that require understanding the formal semantics of the language incredibly well. There are people who are working on that. It's very complicated work. Hung Suk is largely responsible. There's a guy named Ken Shan, if you know him. He's been working on this. He's in Indiana. There are people who are working on, I think this is what you meant by inferring observations, basically figuring out how to move them as far forward as possible. Yes, definitely. Another sort of politician answer that actually is the answer to your question is that I think the most interesting thing, and I shouldn't say this because this is actually what we're working on, is to figure out how to even more generally take, say for instance, a connectionist architecture, hint hint, and map from, sort of learn the inverse mapping from the observation space to the values of latent variables and use them for proposals in inference. Okay? I said it. Eventually, 3 years or 4 years from now when I come back or something like that and we've done it, then maybe it'll make sense. But I think that's actually the answer to your question. There's a couple of them, yeah. You can also just shout them out. I'll just repeat the question. It's fine.
So hi, there's kind of a parallel world to this, if I understand right. Say probabilistic logics that are leading to probabilistic programming languages like Markov logic and alchemy and so on, where it seems like the main inference algorithm issue they dealt with are issues of lifting. So how can you do generalized inference rather than in some ground space? Is there a relationship of that to the kinds of things you're doing here, or are they really just independent worlds?
So we've had the okay, caveat emptor. As a Bayesian, I don't really understand lifting. Lifting to me is exactly the same thing as computing sufficient statistics in a conjugate family. That's exactly what it is. There's no difference. So we had the great honor and privilege of having David Poole run around Oxford for the last year. And he and I have met once a week for the entire time, and he works on lifting and exact inference and these kinds of probabilistic logics and so on and so forth. And as best that we can work out, what I just said is true, and neither of us can figure out how to talk to one another still after having sat in the same room for a year. Okay, so really what lifting says is let's compute on the aggregate. Okay, and in Bayesian statistics, that basically says there's a model in which there's a latent variable that we can integrate out and we have to maintain state, and that is the aggregate. This is a very loosey-goosey, terrible answer to your question. I apologize for that. But as best we can work out, sufficient statistics in an exchangeable model are exactly equivalent to what you can accomplish with lifting, and that's it.
Okay, I think we have time for maybe one more question.
Oh, come on, there's more time than that. This is a coffee break after this. Nobody wants coffee.
So who's do you want to ask?
This is fun. Yeah, there's like 2 or 3 over here somewhere.
Quick one, are your slides available?
Yeah, I can make the slides available, yeah.
Okay, that was short. Maybe another one.
This is more of a future-hearing kind of like conceptual question, but how do you see probabilistic programming evolving in the future with quantum computing? Or is that a relevant question?
I don't understand quantum computing at all, so I can't answer that question.
Nobody else?
But I'd be happy to discuss it with you, if you understand it. Yeah.
Yeah, just a quick question about the performance of the programming languages. If you would do a particle filter, for example,
This is a good question. So let me just say a couple things quickly so that we can answer some other questions. So there's two kinds of complexity, right? So one is all of the deterministic, all of the Fs are compiled. So that the only breaks are at the observes, and you have to break anyway so everything's compiled basically. So it's just as fast. So yeah, definitely don't hand code sequential Monte Carlo particle filter out. Like if you're doing particle filtering, you definitely don't need to do that anymore. That's like no question. The other thing is, if you're asking about what the computational complexity of inference is, then it's whatever the computational complexity of your model is, because we're running that, times the number of particles divided by the number of processing elements. So if you have the number of particles equal to the number of processing elements, which you can on, say, for instance, most GPUs now, then the complexity of inference is the complexity of your forward simulator, basically. So that's about as low as it gets. Yeah.
Maybe one really short one?
There was one over here somewhere. That was, you had your hand up again.
Thanks for the great talk.
Oh, you're welcome. Yeah,
Really
thank you for listening.
Language.
Yeah.
I'm looking at one use of this hammer that would be like inferring the parameters of the scene graph, like in computer gaming, from observed scene sensor data from a camera. So I've seen this in your examples of X-Y combination and inverting this model. Can you tell us a little bit, are there examples already of like scene reconstruction using this model? Because that is something I think that is a sub-problem that's a practical one that occurs quite frequently in AI and robotics, and like being able to access directly the scene graph, and then from there like abstracting objects into a semantic network, we very quickly would, in the AGI community, would get to inferences. Okay. Well, scene graphs are complex, are real scenes. There's like not only one object, there's multiple objects, there is like...
No, I understand. So you asked, your question was, is there work that we could look at? And the answer is, these are the two papers. Okay? And I can tell you what to pay attention to. This one is sort of a philosophical paper. Look, you can do it. You can frame the problem such that it's a nail that you can hit with a hammer. This one is, and this is just one of the examples from these papers. There are many other examples from these papers. This one does, road scene decomposition for automated driving, and this one does, what else do they do? Pose segmentation, pose recovery, and that sort of stuff. They do a bunch of stuff. This one starts to get towards practicality, and what they actually are really working on in this paper is inference. It's a CVPR paper, but what they're really saying is, hey, if we're going to do perception in this way, we need to speed perception. And the most interesting stuff, and I talked to Tejas a bunch about this, the most interesting thing that they've done here is to say, okay, let's use connectionist architectures to speed inference by extracting features that are interesting in the form of latent variables and random choices made in the program, and direct the computation of the program by learned feed-forward architectures computing stuff from scenes. So yes, this is a relatively low parameter count parameterization of a scene. This is something you can put on a slide. But the idea is to work on inference such that you propose program paths from feature extractors, and that's kind of that's the loop. That's the direction that I would look in. So yes, there are two papers, and I would look very, very carefully at the proposal mechanisms that they use in this, because that's how you get inference to actually work. So the language is, it's easy to express the problem now. It's all about inference and making it efficient. Yeah.
Okay, before we all leave for coffee, Richard Mala of the Future of Life Institute has a few words to say. But first, let's thank Dr. Wood again.
And I do make the, I'll speak to whomever, but if any of you, if there's time or whatever, I'm very happy to go through and actually show you a tutorial and teach you how to program in Anglican and that sort of thing. So if there's time, it doesn't look like there is in the conference schedule, but come find me if you want to hang out all night tonight learning how to program in Anglican. All right, cheers, bye.